So you already know that objects can obtain a positive or negative electric charge, and then like charges repel and opposites attract. So these attractive and repulsive forces that charged objects can exert on each other are called electrostatic forces. And electrostatic just means the charges are not moving. So these objects become charged by gaining or losing electrons. For example, when you rub two objects together, there can be a transfer of electrons from one object to the other, making them attract each other. So there are two main types of materials, conductors and insulators. Conductors are materials in which the charged particles can move freely around. For example, in metals, the electrons are just floating around. They can move wherever they want. So here we have a metal bar, and if we put a positively charged stick close to it, then the electrons in the metal bar, which are free to move around, will gather around here because they're attracted to the positive bar. And then since all the electrons are moved over here, it creates a positive charge over here, since there are no electrons. And insulators, which we call dielectrics, do not have free charged particles. However, their atoms can become polarized, which means the electrons in the atoms clump up on one side. So here we have a dielectric. Each of these circles represents an atom. And we have a negatively charged stick over here. So the negatively charged stick will repel the electrons in each atom. So the electrons will try to clump up as far away from the bar as possible. So they will all go to the right side of their atoms. And that means the left side of the atom becomes slightly positively charged. Now remember, the positive charges here are not actually moving. It's just the electrons are moving, and where the electrons leave, it leaves a positive charge there. So we can discharge objects by connecting them to the ground with a wire, because the earth acts like a giant conductor. So say we have an object with excess negative charge. If we connect it to the ground, the negative charge will transfer through the wire into the ground, and our object will be discharged. And objects can also be discharged by water vapor in the air, because they will attract the polar water molecules, and then the water molecules will take the extra charge away. So electric charge is conserved. You can't just create it out of nowhere or destroy it. And it's also what we call quantized, which means it can only change in certain increments. For example, if you're dealing with cash, the smallest increment you can give or receive is a penny. You can't give someone half of a penny. So the unit of charge is the Coulomb, and the smallest increment of the charge is the charge of one electron, which is 1.6 times 10 to the negative 19th coulombs. And, well, an electron is negatively charged, so it would be negative of this. So we call this number the electron charge. And we can find the force that two charged objects exert on each other using Coulomb's law. So it says the magnitude of the electric force is equal to K times the two charges multiplied by each other, divided by the distance between them squared. So notice how it's similar to the Newton's law of gravitation, if you replace the charges with mass and the K with the big G. So the big difference is that the K, the constant here, is 9 times 10 to the 9th. So it's much larger than the big G. And remember, this only finds the magnitude. to find the direction, all you have to do is look at if the two charges are repelling or attractive. So let's say we have three charged spheres in this equilateral triangle arrangement. And charge A is positive 2 times 10 to the negative 9th coulombs. Charge B is also the same charge. And then charge C is negative 4 times 10 to the 9th coulombs. So we want to know what the net force on charge C is, because both A and B will exert a force on charge C. So since the A and B charges are the same, they'll exert the same magnitude of force on C. So we use Coulomb's law and just plug it in. So one of the Q's is 2 times 10 to the negative 9th, and the other one is 4 times 10 to the negative 9th. Notice how I didn't use the negative because it doesn't matter. All we want to do is find how strong the force is, and then we can determine the direction based on if they are repelling or attracting. So in this case, they are attracting each other. So we can draw a force diagram for C like this. And then from the symmetry, we can immediately tell that the horizontal components of these forces will cancel each other out. So all we have to do is find the vertical component of each force and then double that for both of them. So the vertical component for each force is just cosine of 30 degrees times the magnitude of the force. So for both of the forces, it's 2 times the force cosine 30 degrees. So we already found the force, and now we just plug it in and we get that the net force on charge C is negative because it's pointing downwards, 1.2 times 10 to the negative 7th newtons. So imagine you have two positively charged objects next to each other. Well, since they'll repel, they'll start flying in opposite directions. So they randomly gain kinetic energy. But we didn't do any work on the system, so that means the energy had to come from somewhere. It had to use some of its energy that it already had to convert into kinetic energy. So we call the energy that two charged objects have electric potential energy. So if we have two charged objects, then the electric potential energy between them is K, Q1, Q2 divided by E. And if we have a system with more than two charged objects, then we have to count up the total potential energies between each pair. So let's say we have two positive objects separated by 1 meter, and we want to put a third positive charge so that the net force on it will be 0. So we know that we have to put it somewhere in between these two charges, because if it was on either side, then it would just go flying off. So we can call the distance from the third charge to the first charge 1, and from the third charge to the second charge 2. So we want to solve for either 1 or 2. And we know that 1 plus 2 is equal to 1, because that's the total distance between charges 1 and 2. And we also know that Q2 is just double that of Q1. So if the net force is 0, then the force exerted on charge 3 by Q1 is equal to the charge exerted on charge 3 by Q2. So we write the Coulomb's law for both of these forces, where instead of writing Q2, I wrote Q2 Q1, and then we can cancel out the K's and the charge of the third charge, and then the Q1s. And all we have is 1 over O1 squared equals 2 over O2 squared. So then we can replace O2 with 1 minus 1 squared. And then if we take the square root of both sides, we get 1 over 1 equals the square root of 2 divided by 1 minus 1. And then with a little rearranging, we can solve for 1 as 0.41. So the third charge, we need to place it 0.41 meters away from Q1. So if we have this polonium nucleus and this alpha particle that a distance of 1 times 10 to the negative 15th meters apart, and we want to find how fast this alpha particle will move since they repel each other. So we want to find how fast it's moving when it's very far away. And very far away just means we can assume that the potential energy between these two charged objects is 0. So all of the initial electric potential energy that these two objects have is converted to kinetic energy of the alpha particle. So the charge is plus 84e, which means 84 times the electron charge, which is 1.6 times 10 to the negative 19th, and the alpha particle is plus 2e. So we find the initial energy and set it equal to the final kinetic energy of the alpha particle. And if we plug all our values in, then we can solve for V as 1.1 times 10 to the 8th meters per second.